So, hello, welcome, good day, ladies and gentlemen. Welcome to our first webinar of this year. We are excited to be back on air, and today topic of our first webinar of the year will be co-check of steel members with stability issues, and in our case, the horizontal beam with buckling issue. Let me introduce myself. My name is Vlastimil. I am a product engineer within IDEA StatiCa, and I will be moderator for today's webinar. And also, I would like to welcome my colleague Adam, which will take you through this webinar. So, Adam, welcome. How are you? Great, thank you. Okay, so everyone is muted by default, and you will be muted during the whole webinar. But if you have any questions, don't hesitate and ask us. Just type the question in a question panel. We are using the platform GoToWebinar. So let's move on, and let's see what Adam have prepared for today. And before we start, I have created the first poll for you. So I will ask you this question. So how do you treat the stability and buckling checks of members? Either you use advanced software, or you use hand calculations and Excel sheets, or you can use your engineering judgment, of course. And the last option is you don't bother with this issue. Okay, I will give you a few more seconds to answer the question. Great. Okay, so I will close the poll now, and I will share results. So you can see that most of you are using the advanced software for taking care of stability issues. A quarter of you still use the hand calculation or some Excel sheet, and the rest uses the engineering judgment, and only few of you don't bother with this issue. So now, Adam, it's yours. You can start with your webinar.
Thank you, Vlastik, and greeting once again to everyone. I just got a message from Lasse, one of our attendees, that I was muted in the first introduction. So happy to be here with you today again, and I'll take the presenter and I'll start right away. Turn off my webcam as well. So I have prepared for you a presentation together with two demos of the application. And in the presentation, I would like to share comparing two approaches, hand calcs and the advanced software IDEA StatiCa Member, treating these stability issues and checks. So for some introduction, just briefly, when should we actually do this? When should we bother with that? Eurocode, as well as the other codes, is very similar. Imagine you have the structure or the global structure model. You calculate the critical force over the whole structure divided by the load effects. The criteria value is 10. So if you don't fulfill this, the first order analysis is good enough with the initial geometry of the structure. You don't have to bother with these stability issues. If it's over the criteria, you should be aware and should treat the second order analysis, where you consider the deformed shape of the structure, imperfections, stability issues, and so on. So this is yes or no. For standard, let's say standard constructions, simple constructions, it's usually not necessary to do that, of course. Then another thing, when you have to do the second order analysis, which means verification of stability as well, with the imperfections and so on, you have currently, let's say, 3 options how to do that. First option, most advanced numerical methods, finite elements, where you really calculate quite precisely the nonlinear solution with the imperfections included in all the necessary parameters, facts, and so on. Then a second option is, on the other hand, very simple. You just multiply all your horizontal forces on your global model by some factor, for example, 1.2, and recalculate the first order analysis. This is a very simple approach. On the other hand, of course, it usually leads to overkilling the design, over-designing the member cross-sections and so on. Third option, this is the hand calculation or the analytical approach as described in the codes. It's represented by the buckling lengths, determinations, and so on. So that's the tools we have. And speaking about imperfections, what does that mean? Those are all the geometrical deviations from the production of the members. So those are not ideally perfect as in our tabs. Of course, there are residual stresses in those members and so on. And then there are imperfections on the construction side, where when the structure is being assembled, you've got some non-ideal straightness, misalignment, and so on, small eccentricities, different from the ideal drawings that we produce as designers of the structures. And those imperfections, there are 2 types, right? So it's a global imperfection. This means some overall value for the whole construction, represented by, let's say, initial deformation or tilt of the structure. The code describes it with the parameter phi, or the tilt angle of the whole model. This you apply in your global model, for example, in SAP 2000, SIA, or such softwares. And then you have local imperfections, and those are imperfections of each of the members, or bars, of beams, columns, and those are the production deviations and so on. And those are represented by a factor or parameter E0 in millimeters, and that's basically a value describing how big the imperfection is for the specific member. So that's for the introduction, and now let's move on with the, let's say, small experiment or small study that I have prepared for you. We will be comparing the third approach, the hand calculations, using the formulas from Eurocode, determining the values. And against that, we'll be competing with IDEA StatiCa Member, and that represents the first option, the most advanced, completely nonlinear finite element method-based calculation with imperfections and all the other inputs. Right, and we will be comparing these this QBRD value. That's the capacity of the beam against the linear load. The linear load is the design value is 20 kilonewton per meter. We will be comparing the most simple case, probably simple beam with pinned supports, hinges on both sides, linear load, IB cross-section, 235 steel. The span is 3.5 meters. Okay, so this is the probably most simple scenario we can have. And let's move on with the analytical solution. So what do we have to do? We have to determine the design buckling resistance moment. For this, we have some equation. And for this equation, we need a couple of parameters that we have to determine from tabs and other equations. So this is, let's say, kind of step-by-step procedure. For one of these factors, we also have to determine the elastic critical moment. This is all well described. So if we go step by step, we first determine the section properties of our beam, material properties, and then we go to the tab I2, where we find our key or buckling length factors depending on the support rigidity. So since this is completely hinged or pinned beam, we've got 3 ones. As I said, simple scenario. So we can easily read all the necessary values from the tab. Also, we just check the center of gravity and other centers for the cross sections. This is very easy as well. And then we start inputting the parameters and values into those equations and calculating the dimensionless parameters. There's a couple of them. All right, nothing complex, right? Dimensionless critical factor, another nice equation, and finally the critical moment, and then delta LT slenderness parameter. Here we also have to take a look in the tab 6.3 in Eurocode to determine the imperfection factor alpha LT for the given buckling curve, and continue with those equations and calculating these parameters, HLT, and finally we calculate the buckling resistance moment. And this is where we finish this procedure. We've calculated the moment, and this is the resistance moment of the beam, which is objected to the stability losses or stability issues of the lateral buckling. So if I recalculate simply or determine from the value moment on this simple beam the linear load, right? I got value 13.25 kilonewtons per meter. That's the resistance or the capacity of the linear load that the beam can take unless it loses its stability, which is less than the design load of 20 kilonewton per meter. So obviously this beam is going to fail due to lateral buckling, right? So that was the hand calc procedure. Simple, straightforward, nothing complex. Just we need the code and the equations. We can put this in some Excel sheet, and that's fine. Now let's see about another approach with IDEA StatiCa Member. So we have the same beam. Here we are modeling the real part of the structure. So what we have to add is actually the real support, which will be represented by HEA columns. And of course, the span of the beam is between the flanges of the columns. So the theoretical length, axis to axis, is different. It's not 3.5, but it's 3.89. All right. Another thing, the connections that are modeled within IDEA StatiCa Member. So we model the real connections, get the real stiffnesses of the connections. So we have to be aware of that. And this is just a note, a side note, that I'm going to represent the hinge connections by a fin plate. In IDEA StatiCa connection application, you can easily analyze, calculate, and classify this connection by the stiffness analysis, which I have done for this, and this is for you to see that this is really a pinned connection. So let's jump into the member app. This is how it looks, and I'm going to start a new project and lead you through the let's say step-by-step input of the project. Here I just type the name, I choose steel for the material type project. Here I can choose design code, so I'm going for Eurocode. I can change the steel grade. We said it's going to be 235, right? Concrete grade in case we have some concrete blocks, foundations, anchorings, and so on. And we can choose from, let's say, simple starting templates, a beam or column, or we can input general type of any member column, or even frame, or like more complex beams and so on. So I'll go for this simple beam, input the span, and leave the HEA cross-section and create the project. The UI, very similar to IDEA StatiCa connection. So I've got the ribbon, the tabs in above, the 3D modeling space here, and the input tab on the right. So I can see this is some generated template beam. So I'm going to modify, edit this model. First, I'm going to get rid of these side supports, as we call them, the related members. Then I check the columns. Those are the correct cross sections. I just want to avoid any possible small deformations of the columns. I will input them as shorter, just so these columns have now supports 1 meter above and below. Same for the other one. All right, that's for the related members and or the supporting members. Now for the the beam that we are aiming at, I will change the cross section. That was IP 180. So I just choose it from the library of cross sections. That's fine. Now for the loads, we said it's going to be 20 kilonewtons per meter. That's all I have to do. And now the last thing is designing the or adding the connections, connecting the beam to those columns. So I can either click on this cube in the 3D model or in the navigation tree, go to edit the connection. What happens now is that the IDEA StatiCa connection application opens. This is the, let's say, light version of this application. Light in terms that you cannot calculate here. It's just the, let's say, designing tool, but otherwise it works exactly the same. So I'm going to add the fin plate. I can do this using the connection browser or the dynamic templates. So right click, connect me beam to the column. I choose here from templates that are provided for this geometry and set of members. Of course, I can use operations or other ways how to model the connection, but I like this one because it's simple and straightforward. Okay, I've got the fin plate. I can use also the pre-design function to optimize the shape of the fin plate to something reasonable, something good to start with. So that's right. I just change the thickness of the weld because I want to have 4 millimeters all over the whole connections and part of the structure. All right. So save, close, and we can see the connection in the model of the member. I can do the same on the other side. I can also apply the same connection symmetrically, or I can edit this connection and create anything I like. It doesn't have to be the same, of course. It can be anything. I can just weld it directly or add endplate or haunches or anything like that. So I'll just reproduce the same design here. So let's revise this procedure. All right. And that's it. I've got the member modeled. So let's go to Check tab and calculate. So here, calculation or analysis, which is the component-based finite element method, of course, the numerical methods that IDEA StatiCa developed and uses in its softwares. So first, to say the calculation is done or the analysis is done in 3 steps. The first step is materially nonlinear analysis, which is nothing special. It's just calculation of stresses and then determining the code checks of the cross section of the beam, right? So I can see there's not really happening anything special. This beam passes the checks. This analysis is the same as all the softwares for designing and analyzing structures provides, right? But then comes the second step, which is called linear bifurcation analysis. In other words, it's the buckling analysis. And this analysis gives me the buckling shapes and buckling factors of the analyzed beam of my IP 180. So let's see what can we read here. We can see, first of all, the shape. This is the first buckling shape of the beam. I can turn on more colors to see the sum deformation, right? I can also overscale the deformation. So I'm reading now the first buckling shape and the buckling factor in this tab in the results, which is 0.82, which is very low. It's lower than 1. So this indicates me immediately that this beam is not going to pass the checks for stability, right? Because it's lower than 1. Anyways, I can click in this tab on the other shapes and see the second buckling shape, which is this wave, and read the factors. And of course, if we go further and further, we've got higher factors and more crazy shapes of the buckling, such as this one. Is of course overscaled, and this is more or less just theoretical occurrence, which would never take part in reality, right? But this is how it could under some conditions. But let's go back to the dangerous one, shape number 1. All right, so I'm going to analyze further this one with the third step, which is the fully geometrically nonlinear analysis with imperfections, with taking into account stiffness of these connections, taking into account position of load, taking into account all the input parameters of this 3D finite element model. So it's this is actually the most advanced analysis nowadays on table that you can use for such situations. So I switch to this geometric nonlinear analysis, third step, and I will input the imperfection amplitude. That's the value E0 that I mentioned in the introduction in millimeters. I have to determine this one. How do I do that? That's very simple. I jump back to presentations and show you. That's just basically one or two tabs from the code. First tab, you see find the buckling curve based on the cross-section shape and the ratio between height and width. That's probably very well known to all of you. Simple to determine. It's the A curve, right? And then this tab 5.1, that's the one, and that's the crucial tab we need for this. Here we find the A row, and we go for the plastic analysis and determine E0 divided by L, which is the span or the length of the member, and we simply calculate the span, which is 3.5 meters divided by 250, and we've got the value of E0, that's the local imperfection for this beam. So I input this value here, and I'll calculate the this type of analysis. So what we can see now is the finite element solver in action. You can see immediately there's something happening. The iteration process didn't stop immediately at 100%, but the percents are jumping up and down. That means that there is some plastification going on, which is something that we knew before, because in first we did the hand calc and we found out that this beam is losing stability, is not passing the checks, so we know that already. And also we know this on the first side, that the factor that we are now just calculating more precisely was 0.8. That means this beam is not okay, which we can see just right now when we get the results of these geometrical nonlinear analysis. We can see the applied loads stopped at 61.7%. So only 2/3 of these 20 kilonewtons per meter were applied, and at this moment the beam lost its lateral stability. We can see in which shape. If I put back the reasonable scale, you can see it just tilts around its axis in the center, something that we would await, right? Something that we understand, which is very obvious here. But here the results are clear. Beam didn't pass the checks. I see everything. What I can do now, I can go back to design and I can modify the probably design of the connections, strengthen the beam. I can, for example, add some stiffeners here, right? So I can somehow help this beam or this design to overcome the stability issue. But let's leave this for the second part. I will jump back to the presentation and continue with this. So again, the results for this approach, this numerical approach, I can see that the applied load was something about 60%. If I multiply it by this 20 kilonewton per meters, I've got this value, which represents the resistance or the capacity of the beam in terms of linear load, right? You can notice here this percentage is slightly different. It's because I probably didn't match the design of the connection perfectly. I probably chose a different position of bolts or something. And it's because this model is very sensitive to the shape of connections, of course, since it takes into account its stiffness and so on. But of course, the overall results are very similar. So that's just to make it clear for you. And here we have the final comparison. On the left, the analytical or hand calculation, and on the right, IDEA StatiCa Member. We've got very similar results. The main message is that this beam loses its stability, doesn't pass the code check, and the values are very similar, right? What does it mean? We can use both of these approaches. What is convenient for you? This might be fast using some Excel sheet for the hand calcs. Member has one great benefit for me personally, and that's the visualization of the results. So I can see what's going on, how does the buckling shape look like, and I can also print out the report directly and I'm done with the job. Also, I can produce some pictures and so on. So that was comparison of a simple example, right? And now let's move on to a second one, and that would be slightly more complex example. We would have a very similar beam, very similar conditions, but there'll be a few differences. And again, we'll be comparing these hand calcs and IDEA StatiCa Member. So what is the input now? What is different is that we are changing the hinged or pinned supports to some unknown or semi-rigid probably, or unknown rigidity supports. There will be a haunch and an end plate on the left side and a simple end plate on the right side. We've got the haunch on the left side, 200 per 600 millimeters, and we've got two openings in the beam on the right side of the beam. And what's more, we've got a quite intensive local loads on the left side where the hinge ends on the beam, right? So that's, let's say, slightly modified complex variant for that example. Now let's have a second poll, because I mentioned we have unknown rigidity or classification of the supports of the haunch, of the end plate, and so on. So I've prepared a poll for you, and that would be try to determine or try to think of what is the stiffness classification of these three connections, if it's rigid or semi-rigid or pinned. So I'll give you a few seconds. Please carry on with your tips, and I will run the poll right now with possible answers. So please choose the answer that fits you the best, fits the best your tips. I'm not going to read the answers loud because I want to confuse what you have in your head right now. Hopefully you'll find the answer or the most closer answer to what you tried to guess. All right, we've got about 60% of people, of you voting. By the way, there's about 220 of you today, which is very pleasant for us. I'm happy to see all of you here. And 3/4 voted. Let's give it 3 more seconds and close this poll and share the results with you. So we can see that most of you voted that A is rigid, B pinned, C semi-rigid. A third of you went for the last option, rigid, pinned, rigid. So let's see how it is. If you were not successful completely, don't be sad. It was the same for me. I had to use IDEA StatiCa connection and calculate the stiffness using the stiffness analysis. My tips were semi-rigid, pinned, and rigid, but this is the actual state. So I wanted to show you this, share this with you, because This is a very important fact for the hand calculations, where we have to say or determine the stiffness of the supports for the beam, right? Because we need this to choose the correct row or the correct parameters from the tab, right? If you remember, in the simple example, that was very obvious. That was the row where just the ones were for these factors. But since we have some semi-rigid, or even we can't really say exactly just from the design what's the rigidity, it's very very difficult to choose the correct values for the factors. And here I come to another fact for the hand calcs or the analytical solutions. When I tried to do this for this complex example, I ended up going through half of the code, actually, like more than 80 pages. At the end, I was not able to exactly or precisely calculate the code check for this, because I didn't know what's the stiffness of the supports. I didn't know how to treat these openings in the beams. There's no word about this. I didn't know how to implement or how to take care of the local load, which is eccentric to the center of the beam, right? So those are factors that stop me to really 100%ly sure calculate and determine the code check. And here I did this actually for neglecting the local load and neglecting the openings. I did this just a small tab where I used all the rows from the tab that describes the rigidity of the supports. And I concluded with this. So if I did a big mistake, obviously, if I would consider these supports were hinged, I would end up with this value of the resistance. And then if I would proceed, say 1 is hinged, 0.5 is rigid. Yeah. So there's actually also no space for semi-rigid. So I would have to somehow interpolate or guess the other factors from the tab. And here, if I would go to the other hand, the other end of the tab, that means it's fully rigid, these supports, I would end up with this value here. And so you can see this huge spread of the values from 13 to 32. Here there's the limit of 20, didn't pass. So you can see this is there's a huge space for mistakes and errors. So we can completely go over or under, right? So that's very dangerous. And that's why I wasn't able to really be sure about my outputs and results. So that's for the hand calcs, and let's see about how Member can treat this. Obviously, from the picture we can see there is a good way how to do that. So let's see. I'll jump back to the application Member, and I will modify this already designed beam to this new shape. And you will see I can do this easily So I will start with editing the connections. Instead of fin plate, there will be an end plate and a haunch. So let's open that. Again, the application connection opens. I will clear the previous design, and I will use the propose of the connection browser feature and choose this one that's a end plate with haunch and stiffeners. I will just delete those stiffeners because I don't need them there, and edit the parameters of the haunch. We set 200, 600. Just have it, just give it a better shape. 4 millimeters of the weld. Then for the end plate, here I just choose or change the offsets to fit design. Also, I'm going to move the bolts like this. Again, 4 millimeters weld. Right, that's it. I've got the haunch on the left side. For the right side connection, I will edit this as well. Again, I will erase the fin plate and add a simple operation that's the end plate. All right, this shape is just fine. I just keep the 4 millimeters of welds because I want to have it nice. All right, so connections done. What else was different? Load, right? We had this one and also the intensive local load, which was just at the end of the haunch. So if I input it like this and say it was 500, I have the load in position. That's it. And last thing, I want to add these openings. So if I click on the beam, I can add operation here, add openings or stiffeners, stiffening plates or stiffening members, do some welding and cuts as well. But this time I just want 2 openings, and those will be diameter 120. Distance between of them is 300, and they are 3000 at the end of the column, right? So this is for some piping or whatever that could be going through the ceiling beam, ceiling supporting beam, such as this one. All right, so that's it. I can calculate this immediately. I've done the modifications in 2 minutes, calculating right away. Materially nonlinear standard analysis and check of the cross-section shows me all okay, though there is some plastification in the connections, a small plastification of 0.2%, right? So let's move on to buckling analysis and see how the shapes look like. So if I again turn on the sum of the formations to have it in more colors, I can also overscale it So this is now the second shape. So I click on the first one to see something that we would be awaiting. This is not that much different from the first case, right? It's still just a beam supported on both ends, right? So the most dangerous would be the lateral buckling. But let's see about the second shape and note these factor values. Second shape looks like something like this. This is also very reasonable. And then again, we are getting more and more shapes and these unreasonable occurrences. So we can neglect those also with high factors. Those are not going to happen. So let's go back to the first one. That's the most dangerous one. 1.38 means this is still very low, close to 1. So this can be very dangerous. At this point, if I had this information, I would be probably pretty aware of this, and I would probably be, as a structure engineer, not brave enough to let this constructed, right? I would like to strengthen this somehow, or treat this stability, possible stability loss. But we've got now this tool. So again, imperfection amplitude 14, this value stands. Same, because it's the length of the member, the cross section is the same, so there is no change in this case. So let's go further to the third step, and that's the tool to help me to know really exactly and precisely if I can design this and do this peacefully in my mind, or should I modify this design, right? So at this point, this tool, this application tells me, okay, design it or not. And this is a huge value in such situations, right? Because I see now the applied 100% of the loads, so these 20 and this 500, and I can see that I pass the checks, including imperfections, including the possible stability losses, including, of course, the exact rigidities, stiffness values of these connections, of these supports, position of loads, openings, everything there, all calculated, analyzed, and put against the code checks. And I pass it. So this beam is okay, this can be designed, constructed, and I don't have to worry that something wrong would happen. So that's the output of IDEA StatiCa Member in this case. So I go back to the board and conclude this second variant of this slightly more complex example. So with the analytical solution or the hand calcs, I had extreme difficulties to do that. I avoided this approach actually because I wasn't sure if that's correct, because I saw this huge risk of error I could do. On the other hand, IDEA StatiCa Member, I simply designed the model, created a model, calculated, code checked, okay. Fine. So let's conclude this. If I would put the hand calc analytical solution, which is still widely used And note that this analytical solution is often incorporated in your softwares as well. So make sure what are you calculating with your software. Not all of them used finite elements. Some of them used just this analytical solution somehow incorporated using some interpolations for determining the parameters and so on. So make sure this is correct in your cases. And what to say about this? We could see that for the simple case, simple beam, that was actually very good. It performed well. It was very clear, straightforward, fast. We got the result. If we had this in some Excel sheet, that would be a matter of, I don't know, a minute too, right? So it's very still effective, but limited to these simple cases, so where everything is obvious, everything is according to those options given by those tabs and equations. So for complex cases, you would get to the estimations and so on and risks of errors, right, as we demonstrated. On the other hand, against that, there's the numerical, fully nonlinear solution with imperfections and so on. This is might be less convenient for simple solutions. You have to determine just the E0 value, but of course this covers everything possible regarding the design and the inputs. And what's the most important for me personally is the visual check, right? So we saw in IDEA StatiCa Member how do those buckling shapes look like, what's going on in the member, how do stresses look like, right? We could immediately react on what's going on, put some additional support, strengthen the beam, or add some stiffness and so on. And with these analytical solution, we don't have any information of such. We have just one single value that tells us yes or no, but we don't know at all what's going on. We could hardly sometimes react on modifying the design. So that's for me, the biggest value of the software approach. So just concluding with some additional information for you, how use the IDEA StatiCa Member. If we remind about the global and local imperfections, that takes part here. So if we use member as standalone, that's the way I did, just create a model from scratch. Here, we don't have the global imperfections because they are applied on the global structure in your SAP 2000 ETABS, RFM, SIA, or Robot, other softwares, right? And those are represented by the value of the loads that we input into member, and we just apply the load imperfections, this E0 value, right? Then we can do this more wisely and more easily. Just use the BIM link. So we import all the data, all the geometry, and all the loads from these softwares, of course, including the global imperfections from the global model, and we just apply this local imperfection on the member. So that's almost no work after all. And last thing, a couple of examples of what can be done in member. Again, similar to connection, this is not limited in terms of geometry, topology, shape of beams, columns, or even whole frames, of supports, connections, positions of loads, right? So you can do everything. Like you can have, for example, this roof platform where you have these rafters stabilizing the lateral torsion of the main beam. This is, of course, incorporated into the analysis. So I came to an end of my presentation and of my part, so I'm now giving the word back to Vlastik, who will conclude today's show.
Okay, thank you, Adam. Thank you for great presentation. I think it was very useful for engineers and also our customers. I will take back the presenter.
My pleasure.
Okay. So I hope you see my screen. You should see my screen. During the webinar, we had a lot of questions from the audience, and I selected 2 of them. So, Adam, if you are ready, I will ask you the first question.
I hope so.
Great. So the first question is, what are the options for adding loads? Is it possible to put IG on the bottom flange, or to put the load on the bottom flange, or to set the load as eccentrical?
All right. I guess you processed the question this way. So applying the loads, so I will take the presenter and show it. That would be the best. If I go back to the model and to design, I mentioned that with those pictures. For the loads, you can apply them on any part of the beam or its cross section. So, for example, this local or point load here, it plays a role if you put it on the whole across the whole width of the top flange, or for example, if it's on some eccentricity like this, right? So this way you can apply the load eccentrically on the top flange, which has an effect on, of course, losing its stability. You can also input the loads not on the top flange, but for example, on the bottom flange. This has now slightly stabilizing effect. So yes, there are options and quite a freedom of in inputting the loads. Of course, you can input the horizontal loads as well as you wish. So I hope that was the correct answer.
Perfect, thank you. And I will take the presenter back again.
All right.
And
What the other question?
Yeah, the other question which I selected, when checking the linear buckling analysis or running the linear buckling analysis, how do we know whether the member is going to fail or not going to fail?
All right. Let me see. If I quickly calculate this, the linear analysis, the linear buckling analysis gives you information about the shape of the buckling and gives you the buckling factor value, right? So it doesn't tell you about the final code check, but it's, let's say, some kind of middle step between the basic code check and the full code check for the geometrically nonlinear analysis with taking into account the stability and imperfections. But you can see on the first site about this factor for the buckling shape. So if this is lower than 1, then the destabilizing forces on this beam are bigger than the stabilizing or resisting forces, and this beam is going to lose its stability. So we don't need to even calculate this third step, right? If it's bigger than 1, then there is a danger that it could happen if we take into account the imperfections, which of course make it worse. Now, if the factor is about this 2.2, is still quite low, and there's still a danger of losing stability of this beam. If this factor is more than 10, we don't have to take care of these stability issues. So I think that's it. So I don't know, to sum it up once again, buckling analysis, buckling shape, buckling factor. If it's lower than 1, the loss of stability occurs. If it's close to 1, it's dangerous. If it's around 10 and more, it's safe, and we don't have to think of it.
Perfect. Thank you for your thorough answer. So that was it. And what will happen after the webinar? After the webinar, please fill in our short survey where you can write some feedback, so we can explore it later. And this session is being recorded, so after the webinar we will upload the recording in our support center, or you can find it in our support center on our webpage or on our YouTube channel. For those who are not experienced with IDEA StatiCa products and you want to try it, please get the trial version. You can apply also on our website for 14 days trial. And also, if you want to learn something new, if you want to educate yourself and find out more about theory, or if you want to explore the older webinars, please go to our support center on our web page. We are preparing next webinars for you. So the next webinars will be in March. On 16th of March, there will be webinar dedicated to concrete structures, and on the 30th of March, there will be another webinar dedicated to steel topic. If you want to improve your skills in IDEA StatiCa connection, please apply for IDEA StatiCa Campus. You after graduation, you will receive some certificate that you are really experienced and skilled engineer, and it can help you with modeling complex joints and connections. So that's all from our side. So thank you very much for your attendance. Thank you, Adam, again for very thorough and very interesting webinar, and I hope we will see each other in March on our next webinars.
Right. Thanks from my side. Wish you a pleasant day and see you next time.
Okay.
Bye-bye.
Thank you. Take care. Bye.